AP Cram, Calculus AB, Free Response Exam Review, Question 4, Modeling Water Overflow with a Basic Integral. The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t equals 20 the sine of t squared over 35 cubic feet per hour, and t is measured in hours. T is either greater than or equivalent to 0 hours or less than or equivalent to 8 hours. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t is equivalent to negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour, for t is either greater than or equivalent to 0 hours or less than or equivalent to 8 hours. There are 30 cubic feet of water in the pipe at time t equals 0 hours. The pipe can hold 50 cubic feet of water before overflowing. For t is greater than 8 hours, water continues to flow into and out of the pipe at given rates until the pipe begins to overflow. Okay? Right, but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. All right, so I'll give you a moment to think about this and strategize how you would write this. Okay, so in an attempt to model overflow in this pipe, what you're expected to do is set up an equation first using the initial condition. And the initial condition that we're told is that there are 30 cubic feet of water in the pipe at time 0 hours. So before anything starts flowing, there's already 30 cubic feet of water. That's the volume of water that the pipe holds. It might not be the maximum, but that's just the amount contained, okay? So that's what we're going to write out first in an effort to model overflow using calculus. All right, so after your initial condition, you're expected to come up with an integral expression that would incorporate the time w. Okay, so for a time greater than 8 hours, which we're told to denote as time w, and we're also going to incorporate time t equals 0 into our integral expression because these are the bounds, or our limits of integration, okay? So we're integrating from 0 to w. Although we don't know what w is, we're actually told to use w as the variable for the upper bound or upper limit of integration. And keep in mind, we don't have to solve the integral, we just have to accurately express it. Okay, so our integral expression also has to incorporate the holding capacity of the pipe. But before we ultimately express the holding capacity of the pipe, what are we going to integrate? What is our integrand going to be? When I say integrand, I mean the equation of integration. Well, first we have to consider r of t, how much water is flowing into the pipe. So this 30 is going to change due to how much water flows in. And if it's changing due to how much water is flowing in, it's also going to change due to how much water is flowing out. So a flow in is going to be an addition or a positive, and a flow out is going to be a negative. So we're basically integrating r of t, the rate of water flow in, minus d of t, the rate of water flow out. And we're integrating with respect to t. This is our time, because ultimately whatever we integrate with respect to is a dimension that we'll be getting rid of. And if we get rid of time, that's going to be expressed in hours. okay, we're going to be left with cubic feet. Notice D of T is expressed in cubic feet per hour, but if we get rid of the per hour, we're left with cubic feet. Also, R of T is expressed in cubic feet per hour, but if we get rid of the per hour or T, our time dimension, we're left with cubic feet. And that kind of makes sense because this 30 is 30 cubic feet of water. It's the initial volume, okay? So we're good with that. But now we want to ultimately express the holding capacity of the pipe. And we're told that the pipe can hold a capacity of 50 cubic feet of water before overflowing. Okay, so this is our final expression. We've taken into account the initial condition, our integral expression, which includes the time W when the pipe will begin to overflow once it tips 50, so just on the cusp of 50 cubic feet. That's, you can, let that be your overflow point. And the lower limit, which would have to be time 0. You can't start at a time less than 0. Well, you can. I just don't know how to think of it or express it at the current moment, but I'm sure there's someone out there who does. Okay?